Having talked about locks, the next synchronization primitive that we'll talk about is semaphores. So what is a semaphore? For all practical purposes, a semaphore is really an integer variable. But an important distinction of semaphores from regular integers is the fact that besides initializing the semaphore, it can only be accessed using two atomic operations, wait and signal. So essentially, this semaphore variable, it can only be incremented and decremented using these two atomic operations, wait and signal. Here is how the wait and signal functions or operations work. Let's assume that the initial value of the semaphore is 3. So if you call this wait function or wait operation on the semaphore s, it will first decrement the value of s by 1. So the value of the semaphore will change from 3 to 1. I'm sorry, from 3 to 2, 3 minus 1. After decrementing the semaphore, the wait function will check whether the value of s is still greater than or equal to 0. If so, if the value of the semaphore is still greater than or equal to 0 after decrementing, then we can continue and enter the critical section. No need to execute steps 3 and 4 in this case. However, after decrementing the semaphore, if the value of semaphore is now negative, then the calling thread, the thread which has called the wait operation, it cannot be allowed to enter the critical section. The calling thread should be blocked. It would be added to a list of blocked threads and it would be put to sleep. Now this waiting thread would be in sleep until it is turned for this thread to enter the critical section. It is important for you to remember that the wait function is executed atomically. So what that means is all of these steps which are happening, all of these operations that are happening inside the wait function, they will happen all together at once or not at all. So essentially these would be executed without any interruptions, without any context switches. Just like the locks, the semaphores are also used for guarding the critical sections. The wait operation in semaphores is analogous to acquiring the lock. The signal operation in semaphores is analogous to unlocking the lock. Typically, the wait operation would be invoked before entering the critical section, and the signal operation would be invoked in the exit section after completing the critical section. Now let's look at the signal function. When the signal operation is called on a semaphore, this operation will first increment the value of the semaphore by 1. So for instance, if the current value of semaphore was 2, this would first change to 2 plus 1, 3. After the increment operation, the signal function will check whether the current value of the semaphore is still less than or equal to 0. If so, this means there is at least one thread that is waiting upon this signal to enter the critical section. And therefore, we should wake up one of those sleeping and waiting threads and allow it to enter its critical section. Again, remember that this signal function is also an atomic operation, right? So all of these steps inside the signal are executed as one unit without interruption. If the initial value of a semaphore is greater than 1, the semaphore is also known as a counting semaphore. So this is a counting semaphore. You can think of a counting semaphore as a pool of permits. It is useful to have a counting semaphore when we need to guard multiple units of the same kind of resource. So for instance, let's say we have 3 printers. Because there are 3 printers, 3 separate processes can be printing simultaneously in parallel. Now instead of having 3 separate locks L1, L2 and L3 to guard each of these printers, we can simply use one semaphore and initialize it to value 3, equal to the number of printers that we have. And this single semaphore variable will guard all 3 of these printers. So I mean guard access to these 3 printers. So as we have seen in this example, when we are using a counting semaphore, the initial count to which the semaphore is initialized is usually the number of resources that are available in the system, number of instances of the resource. What that means is, if we have, let's say, this semaphore s equal to 3 guarding these 3 printers, each of these printers at a time can only be accessed and used by one thread or one process, but we do not need 3 different locks to ensure that mutual exclusion. If the initial value of a semaphore is 1, then the semaphore is a binary semaphore. If you want to use semaphores instead of locks for providing mutual exclusion, then you can initialize the value of semaphore to 1. By doing this, the semaphore basically functionally behaves like a lock. Now in your code, essentially in the entry section, instead of doing a lock operation, you will be performing a wait operation on the semaphore. On a successful wait operation, you will enter the critical section. When you are done executing the critical section, in the exit section, instead of unlocking the lock, you will signal the semaphore and then execute the rest of your code in the remainder section. Always remember that when you are doing a wait operation on the semaphore, if the value of the semaphore is less than equal to 0, then you cannot enter the critical section. The thread would be put to wait. As opposed to this, if the current value of the semaphore is greater than or equal to 1, then the access to critical section can be granted. As you would have realized by now, semaphores are more versatile as compared to locks. Recall that locks are binary. They are either locked or unlocked. As opposed to this, because a semaphore is an integer, it has greater number of states depending on what is the initial value of the semaphore. You can initialize a semaphore to any integer value including 0 depending on your program logic. Recall, when a thread performs a wait operation on a semaphore and the current value of semaphore is less than or equal to 0, in this case the thread cannot enter the critical section and it would be put to sleep. So essentially what happens here is the thread will give up the CPU and it would be moved to a waiting state. Later on, when some other thread performs a signal operation on this semaphore, the waiting thread would be woken up and it would be moved to the ready queue where it would wait for its turn to execute on the CPU. Although we have talked about this sleep and waking up operations with respect to semaphores, locks can also put waiting threads to sleep. If you want to use semaphores in your C++ programs, you have to include semaphore.h header file. To create a new semaphore variable, use the data type sem_t, and this is the name of the semaphore that you are creating. You can assign any desirable name to the semaphore variable. To initialize the semaphore variable, use the sem_init function call. So the first parameter here is the address of the semaphore variable that you are trying to initialize, and this init, the third variable here, this is the initial value that you want to set the semaphore to, right? So if you want to set the initial value of this semaphore variable to 3, then this init should be 3. Now what is this second variable 0 here, the second parameter 0 here? So this second parameter over here basically specifies whether or not this particular semaphore variable that you have created, whether it would be shared with other processes or it is only going to be shared by the threads in the current process. If the second parameter is 0 as shown here, it means the semaphore variable you have created, it will only be shared by the threads in the current process. It will not be shared by other processes. A non-zero value here would indicate that the semaphore variable is shared with other processes as well. To perform a wait operation on the semaphore variable, you will simply use sem_wait function call and pass the address of the semaphore. And similarly, to perform a signal operation on the semaphore, you will call sem_post function call and again pass the address of the semaphore variable as a parameter. With that introduction to semaphores and locks, let us now take a look at some of the popular synchronization patterns that appear in our concurrent programs. The first of the synchronization patterns we'll talk about is bounded concurrent access. So essentially what this means is, if we want to allow, let's say, up to n threads to be in a critical section simultaneously, this is bounded concurrent access. Now in general, this is not a good idea, especially for accessing shared data items, but this could be useful when we are resource sharing. So for instance, let's say we have multiple instances of the same IO device. So for example, in our previous scenario, we had 3 printers. So if we want to share these 3 printers simultaneously with the concurrent processes, that can be done with the help of bounded concurrent access. So we can allow up to 3 processes in this case to print their jobs simultaneously on these three printers in parallel. So to provide such kind of access, we'll typically use a semaphore, and this would be initialized to the number of instances of the resource that are available. So for example, if three printers are available, we'll initialize our semaphore to 3. Now let's assume that printing the job, this is our critical section. So access to this critical section would be guarded by the wait and signal operations on the semaphore. In the entry section, before entering the critical section, before printing the job, a process or a thread would perform a wait operation on the semaphore. After performing the wait operation, if the value of the semaphore is still greater than or equal to 0, then the process can enter the critical section and print its job. And when it is done, in the exit section, it will perform a signal operation on the semaphore, which will wake up any other waiting threads to enter their critical section. This is how bounded concurrent access works. Next is signaling. Signaling basically means that we want to force a section of code in one thread to run before a section of code in some other thread. So for instance, let's assume that statement S1 in thread T1 should be executed before statement S2 in thread T2. One way of enforcing this requirement is with the help of a Boolean variable and busy waiting. So let's say we define a Boolean variable b and we set it to false. Now in thread T2, before we can execute statement S2, we have this busy while which is spinning on this Boolean variable b. So this is while not b. So essentially, as long as b is false, this statement would be true, and the thread T2 would keep spinning in this while loop. It will not be able to proceed to statement S2. And in thread 1, what we have done is we execute statement S1, and after executing S1, we'll set b to true. As soon as thread T1 sets the variable b, this global Boolean variable b to true, this while statement would compute to false, and thread T2 would be able to proceed and execute statement S2. So this is one way of enforcing the requirement that S1 executes before S2. Now this solution that we talked about on the previous slide, this might work, but there are some downsides of using this kind of signaling implementation. So one important drawback here is, you see this thread T2 is using busy waiting, right? So it is spinning in this while loop without doing any useful work, constantly checking for a value to change. When a thread is busy waiting like this, spinning in a while loop, even though it is not doing any useful work, it is using the precious CPU cycles. So these CPU cycles are being taken away from other processes which may wish to use the processor for some useful computations. So this is one important downside. Now another downside from the correctness perspective is, what if, let's say, this thread T2 had a higher priority than thread T1. So in that case, essentially, unless one possible way of executing or scheduling them would be this thread T2, which has a higher priority, it would typically be scheduled before thread T1, and until it finishes, thread T1 may not get a chance to execute on the CPU. So this may lead to some kind of a deadlock where T2 continues to wait for this variable to become true, but T1, which is responsible for setting B to true, never gets to execute before T2. So this is another possible downside of this implementation. A better way of implementing signaling is by using semaphores. So let's say we define a global semaphore S and we initially set it to 0. So let's assume that thread T2 gets to execute first. It comes in and it performs a wait on the semaphore S. This wait will decrement the value of S by 1. So this semaphore now becomes -1. And because after the wait operation, the value of this semaphore is negative, this calling thread T2, this would be put to sleep and move to a wait queue. Next, so this S2 would not be executed. Next, let's say thread T1 is scheduled. So T1 comes in, it executes this statement S1, and then it will perform a signal operation on semaphore. So at this point, recall that semaphore is -1. So when performing a signal operation, that would increment the value of this semaphore by 1. So now the semaphore becomes 0. So because this value is less than equal to 0, What this means is at least one of the threads is waiting on this semaphore. So this waiting thread T2 would be woken up, and now it will get to execute, so it can move on and execute statement S2. So this implementation using semaphores is a cleaner and more elegant way of enforcing the requirement that statement S1 in T1 gets to execute before statement S2 in thread T2. Note that with semaphores there is no busy waiting, because a waiting thread would be put to sleep, and therefore it will not use up CPU cycles. Next, we'll talk about some challenges and considerations in multi-threaded software development. One of the most important challenge in multi-threaded programs is testing. Now, in general, you would have seen from your prior experience with single-threaded programs, if you give the same input, your program typically produces the same output. But that is not necessarily the case with multi-threaded programs. The same input can produce several different outputs depending on the order in which threads were scheduled. And recall, the thread scheduling order is beyond your control. It is typically determined by the operating system. Ideally, to ensure that your implementation is bug-free and works correctly, you should be testing a given input combination with as many different thread schedules as possible, if possible with all possible thread schedules. When you are testing your multi-threaded programs, essentially you are checking that there are no race conditions, there are no deadlocks, and there is no starvation. All of this needs to be avoided in a correct implementation. For testing, you can either do this manually by creating several different test cases, or you could also use some automated tools to help you detect data races. So there are tools like Hellgrind, which is essentially a tool for detecting synchronization errors in C++ programs that use the POSIX threading primitives. Perhaps one of the most promising things about a multi-threaded program is that multi-threading can actually improve performance on multi-core architectures. Now this happens because different threads inside the same process can be running on a different core simultaneously in parallel, and therefore the multi-threaded program exploits the true parallelism that is available in our hardware. However, note that to see excellent performance improvements, the software has to be designed and optimized to run on multiple cores. If you blindly convert a sequential, which is basically a single threaded program, into a concurrent program by just having one thread or maybe two threads without properly distributing the work between the threads, then that approach is not going to work very well. So let's say you have a naive implementation of your process which has two threads, let's say T1 and T2, and for some reason, let's say your thread functions are such that 90% of the work is done by T1 and T2 is only responsible for 10% of the work. This implementation will not give you much gains. Similarly, if let's say one of the threads is blocked or is waiting for the other thread to finish before it can proceed. So again, these even though your program is multi-threaded, it's essentially going to run as a single threaded performance. It will give you a single threaded performance. So we have seen that properly implemented multi-threaded program is essential to see good gains from parallelism, from multi-threading. Having said that, sometimes even if you have an excellent implementation and optimization, it is possible that certain programs do not benefit from being multi-threaded. Now this could happen, for example, because let's say the problem that your program is solving, the computation problem itself, is too sequential. And therefore, even though you might have broken down the tasks or the work between several threads, it is possible that thread 2 is waiting for the output of thread T1, right? Similarly, thread T3 is waiting for the output of thread T2 before proceeding. So essentially this kind of multi-threaded implementation would essentially run as a single threaded process. You will see very similar performance to a single threaded implementation. And that's not because of your implementation, but that's because inherently the problem itself is sequential. The algorithm to solve the problem is sequential. Similarly, if there are a lot of dependencies and communication overheads between these cooperating threads, in that case also the performance would suffer and you will not get sufficient performance in the multi-threaded implementation. Before moving on, just for your information, here is an example of a problem which is not very friendly to parallelism. Skyline matrix inversion. No need to worry about what exactly this problem is. This is just for your information. We have seen that one way of implementing multi-threaded applications is by using libraries like pthreads. Some higher level libraries are also available that can automatically create threads for parts of the code which can be parallelized. Some examples of these libraries are OpenMP, Intel, parallel building blocks, and so forth. By using such libraries, we can see moderate speed ups in our code, in our processes without much effort. The details of these higher level libraries are beyond the scope of our course, but to give you some idea, the way this works is the section of code that can be executed in parallel is marked with the help of some preprocessor directives. Now, based on these directives, at the runtime, a master thread will fork a specified number of slave threads, and the system will divide the task among these threads. After this point, the threads will run concurrently. The runtime environment will allocate these threads to different processors. After the execution of the parallelized code, the threads will join back into the master thread. So that is a quick summary. In general, if you're writing a parallel or a multi-threaded program for a multi-core architecture, here are various challenges that you would encounter. Managing the shared memory between cooperating processes or cooperating threads, which also is related to proper process or thread synchronization. This is a challenge. As we have seen, when multiple cooperating threads or processes are working with and modifying the same shared piece of data, data races and race conditions may arise, which may give rise to inconsistent results if not implemented and handled properly. So that is a challenge. Another important challenge is with respect to load balancing. So if there are, let's say, 4 cores in the multi-core CPU, ideally for best results, you would want each of these cores to be doing about the same amount of work. So you would want to divide the task, the original task, computation task, such that all the cores have roughly equal amount of work. This will lead to the best performance overall. However, this is not always possible, or this is not always straightforward for many computations for several reasons. So for example, first of all, a given computation task may not be cleanly dividable into, let's say, 4 pieces or roughly 4 equal pieces, assuming, let's say, you have a quad core processor. So it is possible that inherently a computation task is such that some of the cores will do more work than the others. Now, some tasks are also inherently sequential. So what that means is it doesn't matter how many cores you have or how many CPUs you have. These tasks for most part would only be using one core. So again, achieving good load balancing for such tasks is difficult. Also, if you have an asymmetric multi-core processor where all the cores are not equally capable, so it is possible that different cores have different execution speeds. So in this case, enforcing load balancing and extracting the maximum out of the system would be even more challenging. And finally, testing and debugging a multi-threaded implementation or a parallel implementation of a algorithm is much harder as compared to the corresponding single-threaded implementation, mainly because of these several constraints and also because of the possible data race conditions that may arise and other process and thread synchronization requirements. We have seen that multi-threaded implementation or multi-threaded programs have several benefits over single-threaded programs, especially in terms of performance. So on a multi-core architecture, for instance, a multi-threaded program can harness true parallelism. However, it turns out that multi-threading can improve performance not only on multi-processor machines, but even on a machine that has a single core. So let's assume we have a process and there are several threads inside the process. Let's say that right now thread T1 is executing. So T1 is executing and let's say T1 is downloading a huge graphics file. This is taking a while and thread T1 gets blocked for this IO operation. Now in this case, fortunately, if we have other threads within the process that are ready to run, this thread T1 can maybe blocked, but we can start executing these other ready threads, maybe T2 or T3, and keep the CPU busy. So there are two advantages here, right? So first is the user of the process, even though one of the threads is blocked, may still see that the process is responding because the other threads are executing. So the process is more responsive. That's one advantage from the user perspective. And the second important advantage here is increased CPU utilization. So the other threads that are ready to run, they can keep the CPU busy. So overall CPU throughput would increase. Now for this reason of increased CPU utilization, in most modern multi-core machines, inside every core there is typically support, there is hardware support for keeping multiple threads active inside the core. So for instance, inside a core, if there is support for keeping 3 threads active simultaneously, if one of the threads blocks, for let's say one of the threads T1 was executing on the core, and let's say it had a miss in the cache, and now it has to go get the data from the main memory, which is going to take, let's say, 30 cycles. Now in the meantime, when thread T1 is waiting for the data to come from the main memory into the cache, the other threads T2 and T3, which are ready to run and active inside the core, they can keep the pipeline of the core busy. So essentially the core can start fetching instructions from the other ready threads T2 and T3 and keep the pipeline busy. So in this way, even a single core can benefit from a multi-threaded application. So how do you go about designing a multi-threaded program? Essentially, you need to divide the functionality of an application among various threads. So you would need to identify the independent tasks within a program, and essentially each thread can execute a different independent task. This is the high level idea. Now here are some examples illustrating this concept. For instance, let's say you want to design a multi-threaded word processor. So one possible way of doing this is you can divide the tasks, everything that needs to happen inside a multi-threaded word processor among 3 threads, right? So thread 1, for example, can be responsible for displaying graphics. Second thread can be responsible for monitoring and responding to keystrokes from the user, and the third thread can be responsible for performing spelling and grammar checks. Similarly, let's say you want to design a multi-threaded web browser. So once again, you can identify independent tasks that need to happen inside the web browser and divide them across different threads. So for example, thread 1 can be responsible for displaying images or text in the web browser. Another thread can be responsible for retrieving data from the network. So in general, whenever you are designing a multi-threaded program, just think of what are all possible independent tasks in your program that can largely happen in parallel, and then simply implement each of these tasks as a separate thread in your program. This picture over here illustrates the design of a multi-threaded server architecture. Recall, we talked about this multi-threaded server at the beginning of this unit and used it as a motivation for multi-threading. So essentially, in a multi-threaded server architecture, we have a server process which is continuously listening or waiting for new client requests. Whenever a client sends a request to this server, in response to this request, the server will create a new thread to service this new request. So this request that was received, it would be forwarded to this newly created thread, and the server will resume listening for additional client requests. And this newly created thread will service the received client request in parallel. This procedure of creating a new service thread to serve the incoming client request would be repeated for every client request that is received by the server. Pipeline computations can also benefit from a multi-threaded implementation. So for instance, let's say you have divided a computation into various pipeline stages. So in this case, each stage of the pipeline can be implemented as a thread. So let's take this simple example to understand. So let's say we have a real-time surveillance camera which is deployed on a property, and we want to guard this property against any unwanted intrusion. So let's say we have an automated software which is continuously processing the images that are captured by this surveillance camera to find any unwanted intrusions from humans or wildlife on the property. And whenever an unwanted intrusion is detected, we want to set off an alarm. So this is the high level idea or goal. Now for efficiency purposes, we have decided to implement this automated software which is processing the images from the surveillance camera as a pipelined implementation. So let's assume there are three stages in this pipeline: a digitizer stage, a tracker stage, and an alarm stage. So briefly, the way this works is an image frame that is captured by our surveillance camera that would be fed into the digitizer module. As the name implies, this digitizer module would digitize the image for further processing. The output of the digitizer module is fed into the tracker module. The tracker module would process this digitized image frame to figure out whether there is any unwanted human or presence or wildlife presence on the property. The results of this tracking would be fed into the final alarm module, which would process these outputs from the tracker module and if warranted would set off an alarm. So in this case, this digitizer module, this tracker module, and the alarm module, these three modules inside these three stages of the pipeline, they can be implemented as three threads. So we can have a digitizer thread, a tracker thread, and an alarm thread, each of them running the respective stage of the pipeline. So essentially, with a multi-threaded implementation, all of these stages of the pipeline and the surveillance camera could be working in parallel. So for example, this surveillance camera, let's say, is capturing frame number 10. In the same time, the digitizer module would be processing frame number 9, the previous frame, right? And then similarly, the tracker module at the same time in parallel would be working on frame 8, the earlier frame which was digitized by the digitizer module. And likewise, frame 7 would be under processing in the alarm thread. So the multi-threaded implementation would, in this case, would allow us to run various stages of the pipeline simultaneously in parallel, boosting our efficiency and overall throughput of the pipeline. So another application of multi-threaded programs could be in parallel computations. The idea here is, let's say we have a huge computation task. So we can divide this computation task into various smaller subtasks. Each subtask can be assigned to a thread for execution in parallel. And in the end, when all the threads are done, the results from each of these threads can be collected and combined for the final answer. So let's assume that, for example, let's assume that we have a huge array of integers and we want to add all the numbers and find the total of all these numbers inside this array. So let's assume that we have, in this array, we have 4 million numbers. So the array indexes will go from 0 to 4 million minus 1 at the end here. One way of dividing this huge computation task would be, let's say we break down this entire array into 4 equal quarters or 4 equal parts. Thread T1 can work on adding the numbers in the first quarter. Thread T2 can work on the second task of adding the numbers in the second quarter. Thread T3 can add the third quarter, and thread T4 can add the numbers in the fourth quarter of this array. And because these are threads, they can be running in parallel. Once these 4 computations finish, we can actually combine the results by adding the results of these 4 threads and get the final number, the final sum total of all the numbers in the array. So let's say this is the first quarter of the array, this is the second quarter A2, this is the third quarter, and this is the fourth quarter A4. So this thread T1 over here can work on adding all the numbers in the first quarter of the array. Thread T2 here can similarly work on adding all the numbers in the second quarter of the array, and so on. So these 4 threads, T1, T2, T3, and T4, can work on these 4 subtasks in parallel. So let's say thread T1 comes up with the sum of 1 million. So this is the total that T1 came up for the first quarter of the array. Similarly, let's say thread T2 came up with a total of 2 million, T3 came up with a total of 3 million, and T4 came up with a total of 4 million. So we can collect these numbers 1, 2, 3, and 4 million and combine them to get the original total. So essentially, by adding these subtotals from the 4 threads, so 1 million plus 2 million plus 3 million plus 4 million, which is 10 million, we can get the final answer. The 10 million in this case would be the overall total of the 4 million numbers in the original array. Alright, so you would recall just now we talked about a multi-threaded server architecture. We have seen that whenever this multi-threaded server receives a request, it creates a new thread to service this new incoming client request. So while creating a new thread is certainly superior, it is better, more efficient than creating a new process. However, this multi-threaded server that we talked about, it has some potential problems. So the first issue is we have seen that whenever there is a new incoming client request, the server will create a new thread to service this request. So anytime there is a new request, there is some latency in creating this new service thread for serving the request. Now, although creating a thread is faster than creating a process, nevertheless, it takes some finite amount of time. Also consider the fact that once a client request is served, the server thread is discarded. The second important issue with our multi-threaded server is that every time we receive a client request, we create a new thread to serve this request. So essentially, we have not placed a bound on the total number of threads that can be concurrently active in the system. So you see our systems, our server machines, they have finite amount of resources. So unlimited threads could actually exhaust the system resources. For example, the CPU time or the main memory space. So how do we fix these problems? Well, thread pools provide a solution to these problems. So the general idea behind thread pools is that we create a number of threads at the beginning, at the startup of the server, and place these threads into a pool. And these threads will basically sit and wait for work in this pool. This is called the thread pool. With thread pools in place, whenever the server receives a request, instead of creating a new service thread, the server will simply submit this request to the thread pool and resume its waiting for additional requests. Now from here onwards, if there is an available thread inside the pool, then that thread would be awakened and the request would be served immediately by this thread in the thread pool. However, if the pool, let's say right now, when a new request arrived or a new request was served from was forwarded from the server into the thread pool, at this point, if there is no available thread in the pool, then the task would be queued until there is a thread in the pool which becomes free to serve this task or this new request. Also, for the threads in the pool, once the thread has completed serving a request, it will return to the pool and wait for more work. It is not discarded. This picture over here illustrates the working of thread pool. So this queue, the task queue, is basically the queue of client requests that are received by the server, and this is the pool of threads, worker threads, that are ready to serve any incoming requests. So the way this works is an available thread in this thread pool would fetch the next task from the task queue, and it would serve this request or complete this task. When the task is completed, the thread would return, the worker thread would return back into this thread pool, and it can then work on the next task in the task queue if there is any available task there. If not, then the thread would simply wait for more work in the thread pool. Thread pools offer us a bunch of advantages over the previous approaches. So for example, the first main advantage is with thread pools, we already have several existing threads waiting for work in the pool. So we do not have to create a new thread for every incoming request. And usually it is faster to service a request with an existing thread as compared to creating a new thread and then destroying it. So that's one advantage. The second advantage here is thread pools allow us to place a limit on the number of threads that can exist at any one point in the system. So for example, we can limit the size of the thread pool to, let's say, 1000 threads. So in this case, there cannot be any more than 1000 worker threads present inside the server. This is just a example. Depending on the system resources and how many threads can be executed in the system, this number can change. And finally, thread pools also result in better performance across various requests which are of varying sizes, because thread creation overheads are restricted just to the initial creation of the pool. We don't have to undergo the creation and destruction overheads for every request in the system. Alright, so we have been so far discussing the multi-threaded processes or the parallel implementations, mostly in context of multi-threaded programs that execute typically on a single multi-core processor. However, parallel computations are not just restricted to a single multi-core processor or a single multiprocessor inside a computer. Modern supercomputers, they consist of thousands of general purpose processors with the purposes of running massively parallel programs that perform huge computations. So on such supercomputers, when cooperating processes or threads are executing on various different thousands of different cores or CPUs, which may not all be sitting on a single inside a single computer box, the cooperating processes need to use message passing to communicate with each other, to share the data, and also to synchronize. With message passing on such architectures, communication between the CPUs is much more time consuming as compared to communicating between the threads using shared memory on a single CPU or a shared RAM. And therefore, if we want to maximize the performance, if we really want to get the parallelism gains, it is important that we are able to minimize the communication between cooperating processes and threads executing on different CPUs. Ideally, the requests or tasks that share data, they should be assigned to CPUs that are in close proximity to each other. So if possible, to two cores that are on the same inside the same chip. So that would be the closest proximity. So in general, there are some additional performance requirements that we need to account for, especially in for harnessing performance from such supercomputing machines. So for example, ideally, to minimize the communication, when we have divided the tasks between various processors, it would be best if there is no communication until the end of the tasks. So this is typically what happens in search engines. Similarly, to reduce the communication latency, it is important that there is a high bandwidth path between the cooperating CPUs. So these are some additional performance requirements in software as well as in hardware that we need to keep in mind when designing solutions for massively parallel supercomputers with thousands of general purpose CPUs. Alright, so with that background on multi-threaded software development, we are now ready to start talking about some classical synchronization problems and their solutions. So here are two classical synchronization problems that we'll be talking about in this part of the unit. So we'll talk about the reader's writer problem and also the dining philosopher's problem. When we talk about them, some of these may not actually look related to computer science. However, you should know that these classical synchronization problems are examples of a large class of concurrency control problems in computer science, and these are typically used for testing nearly every newly proposed synchronization scheme that comes out. The first synchronization problem that we'll talk about is the reader's writer's problem. So imagine that we have a shared data set, and this data set is shared between a number of concurrent processes or concurrent threads which are competing to use or access this data set. Now all of these competing processes or threads can be divided into two types, right? So there is reader processes and there are writer processes. The reader processes, they only read the data set. They do not modify the data set. They do not perform any updates or writes on the data sets. As opposed to this, the writer processes, they can do both read as well as write on the data set. So they can read the data set. They can also modify or update the data set. So essentially, the problem is we need to allow these various readers and writer processes to access the dataset in a manner such that it does not lead to any data races or any inconsistent results. So essentially, we can allow multiple reader processes or reader threads to read the dataset simultaneously. So you see, if there are, let's say, 30 threads that are simultaneously reading the database or this shared data set, then none of them is modifying the data set, and so that is not a problem. There would be no data race, there is no inconsistency possible. So as many readers as we like, they can be reading the data set simultaneously. However, at any point in time, only a single process or thread can be allowed to write into this shared data set. If multiple threads or processes update or modify the dataset simultaneously, this could lead to data races or race conditions and inconsistent results. Even if one thread is, let's say, writing into the dataset and any other thread is reading the dataset, this could still lead to data races. Therefore, if any process or thread is modifying the dataset, then only that process or that thread can be allowed to access the dataset at that point. No other thread or process can be allowed to access the dataset simultaneously. So this is what we want to achieve. We want to be able to allow multiple reader processes or reader threads to access the dataset simultaneously, but anytime a thread or process is modifying the dataset, that should be the only process accessing the dataset. No other reader or writer can be allowed together with a writer process. Now, in literature, there are many different solutions of this readers and writers problem. All of these solutions involve some form of priorities. So essentially, some solutions prioritize the readers, some other solutions prioritize the writer threads. So here we'll talk about one of those various solutions, and later on we'll see which one it prioritizes, whether it prioritizes readers or writers. So here is all the data that our solution would use. So first here is the data set, right? So this is the shared data set that various reader and writer processes are competing for. Next, for this solution, we'll be using two semaphores, right? So we have these two semaphores. So we'll have a semaphore read write mutex and a semaphore mutex. Both of these semaphores would be initially initialized to a value of 1. And finally, we have this integer variable read count, which is initially initialized to 0. So as we'll see later, this read count variable is used to keep track of currently how many reader threads or reader processes are reading the data set. So here is some more information about the shared variables in our solution. Like we have seen, the read count, which is initialized to 0, it keeps track of currently how many reader processes are reading the shared data structure or the shared data. The binary semaphore mutex, which is initialized to a value of 1, this is used to ensure mutual exclusion when this read count variable is updated by the reader processes. So essentially, anytime a reader process enters its critical section for reading the shared data, it will increment the value of read count. Similarly, anytime a reader process exits its critical section, it will decrement the value of the read count. So this way, the read count will always accurately reflect how many reader processes are currently reading the shared data. Now, to ensure that when these various reader and these various reader processes, they are incrementing and decrementing the read count variable, there is no data races for incrementing and decrementing this read count. So for that, this semaphore mutex is used. So before modifying this read count variable, a reader process or a reader thread must acquire this semaphore mutex by executing a wait on this mutex. And when done incrementing or decrementing the read count, the reader process will perform a signal on the mutex. And finally, the read write mutex. This semaphore is common to both the reader and the writer processes. Essentially, this read write mutex is used to provide mutual exclusion for the writers. So you can think of this read write mutex as a lock that a writer process must acquire before it can enter the critical section and start modifying the shared data. This read write mutex, this also needs to be acquired by the first reader process that enters its critical section to make sure that once the reader has entered its critical section, started reading, no other writer can also enter and start modifying the shared data. Similarly, when all the readers are done reading and this last reader exits its critical section, the last reader will then perform a signal operation on this read write mutex to indicate so that any writers that might be waiting to enter the critical section, they can then proceed and enter the critical section. So here are some implementation notes about the solution that we are going to talk about. Let's say when the first reader thread is trying to enter the critical section for reading the shared data, and there is already a writer in its critical section which is writing or modifying the shared data. So in this case, this first reader thread, this will block on the read write mutex semaphore, and any other reader threads who also try to enter the critical section, they will also block, but they will block on the mutex semaphore, not on the read write mutex, as you will see later. Like we have discussed earlier, the last reader thread that exits the critical section, it will signal any waiting writers to enter into the critical section. Now, whenever a writer thread or writer process exits the critical section, let's say there are both reader and other writer threads that are waiting to enter into the critical section at that point. So in this case, whether a reader thread gets to go next or a waiting writer thread gets to go next, this depends on the scheduler. This is not determined by our solution. Now let's assume that a writer thread exits its critical section, and out of all the waiting threads, somehow the scheduler selects a reader thread to go next and enter the critical section. So in this case, as soon as the one reader thread is allowed to enter the critical section, all other readers that might also be waiting will fall through. Because recall, if multiple reader threads are simultaneously reading the shared data, there is no data race that does not cause any problems. And so if one reader thread enters the critical section, all other reader threads can be allowed immediately. Now, once we have walked through the implementation of this solution in code, we'll think about and discuss whether this solution guarantees progress for all kinds of threads. In other words, whether this solution makes sure that no reader or writer thread would ever starve. So we'll think about this. An alternative desirable semantic that might be possible in an alternate solution would be, as soon as a writer thread is ready to perform a write or modify the shared data structure, we should allow it to enter its critical section as soon as possible. Now this semantic is not provided by our solution, as you will see. Now this slide over here shows the structure of our writer process. Imagine that this is the critical section of uh, the writer process. Essentially in this piece of code, this is where the writer process modifies the shared data item, and this is happening inside an indefinitely running do while loop. Now we need to fill in these blanks to appropriately to ensure that in every iteration when this writer process is modifying the shared data, it is the only one allowed in the critical section. Recall that read write mutex was the semaphore which is initialized to 1, and this is the semaphore which is used to enforce mutual exclusion between the writer threads. So here basically before entering the critical section, this writer thread needs to wait on the read write mutex semaphore. If the current value of this read write mutex is 1 when the writer thread performs this wait operation, then this wait operation will decrement the read write mutex from 1 to 0, and the requesting writer process can enter its critical section and perform writing. Any subsequent writers or readers who try to enter the critical section while a writer thread is inside the critical section, they would, when they perform a similar wait operation on the read write mutex, they would be blocked here in this statement. So that would ensure mutual exclusion. At a time, only one writer thread would be allowed inside the critical section. When this writer thread is done modifying the shared data, it will perform a signal operation on this read write mutex, and any other waiting threads, reader or writer threads that are waiting on this read write mutex, they would then be allowed to proceed into the critical section. So this is the structure of the writer process. It is also shown over here. Now this slide over here shows the structure of a reader process. Let's assume that this portion here, this is the critical section of a reader. This is where it is reading the shared data. And this critical section needs to be guarded appropriately by using several semaphores. So let's try to fill out these blanks over here with appropriate semaphores. Recall this read count variable, which is initially initialized to a value of 0. This keeps track of how many threads, reader threads, are currently reading the shared data. So before entering its critical section, every reader thread increments the value of the variable read count. Further, recall that because multiple reader threads are incrementing and decrementing the read count, the modification of read count itself is guarded by this mutex semaphore, which is also initialized to 1 initially. Therefore, when a reader thread is ready to enter its critical section, it will first perform a wait operation on Semaphore Mutex so that it can increment the read count. Now let's assume that mutex was available, so the reader thread can acquire this mutex. It will increment the read count. Now after incrementing the value of read count, if it turns out that the value of read count is 1, this indicates that the current reader is the first reader that is trying to enter the critical section. Now recall, the first reader, in addition to waiting on the mutex, also needs to wait on the read write mutex, which is used for providing mutual exclusion among writers, because the first reader needs to make sure that there are no writers performing writes inside their critical section before entering the critical section and reading the shared data. So if this is the first reader process, it will further perform a wait on the read write mutex to gain access to the critical section. Let's assume that right now there are no readers or there are no writers in the critical section, so the read write mutex is available. So in this case, this wait operation will succeed. So now the reader process can enter its critical section. So before entering the critical section, the reader process will signal this mutex so that any other reader threads that may like to enter the critical section, they can simply increment the value of read count and directly jump into their critical sections. Note that this waiting on read write mutex is performed only by the first reader thread. It will not be performed by any subsequent reader threads that enter the critical section. Any subsequent reader threads, they will only increment the value of this read count variable. So let's assume that the reader thread enters the critical section, performs the reading. When it is done, it would need to, and it exits the critical section, basically it would need to again decrement the read count so that we have an accurate value of how many readers are currently in the critical section. So recall, to update this read count, again this read count is guarded by this Semaphore mutex. So before performing a decrement of the read count, we must wait on this mutex to ensure mutual exclusion. So the reader thread will wait on this mutex. When the access is granted, when mutex is available, the reader thread will go ahead and decrement the value of read count. Now after decrementing read count, it will check whether the value of read count has gone down to 0. If so, this means the current reader which is exiting the critical section is the last reader. After this, there are no other readers in the critical section, and therefore it is the responsibility of this last reader to perform a signal on this read write mutex, right? This is the semaphore on which other writer threads might be waiting to enter the critical section. So now that the last reader has exited, any other writer threads that might be interested in entering the critical section, they can go ahead. So that's why the last reader thread exiting the critical section will signal the read write mutex here, and then when this is done, it will also signal this mutex to release the lock on read count, and then we are done. The solution is also summarized over here. So like we have seen earlier, there are multiple variations of this readers writers problem. There are two popular ones. The first one, which we have actually talked about just now, in this variation, no reader is kept waiting unless there is a writer already performing writes in its critical section. So we have seen that in our solution, as soon as at least one reader gets to enter its critical section, all other readers can fall through, even though there might be other writers who are waiting ahead of these late coming readers. As long as at least one reader is inside the critical section, any other reader can simply fall through. So this is the first variation. The second variation of this problem is where the writers, once a writer is ready to write, that writer is allowed to perform its write as soon as possible. So this is the second variation. We have not implemented that one. So in other words, if a writer is waiting to access the shared data, no new readers may start reading. So that's the second variation. Regardless of which variation you implement, both variations may lead to starvation. So if you are prioritizing readers, writers may starve. If you are prioritizing writers, readers may starve. So to avoid starvation, there are other implementations. We are not going to talk about those starvation free implementations here in this lecture. However, I must tell you that on some systems this problem is solved by the kernel by providing reader writer locks. Let's talk briefly about the reader writer locks. A reader writer lock can be acquired in two modes. We can acquire it in read mode or in the write mode. If a process wishes to only read the shared data, then it can request the reader writer lock in the read mode. As opposed to this, if a process wishes to modify the shared data, then it must request the reader writer lock in the write mode. Now the way this works is multiple processes are permitted to concurrently or simultaneously acquire a reader writer lock in the read mode. However, only one process may acquire the reader writer lock in the write mode because exclusive access is required for the writers. In pthreads, if you are interested in using the reader writer locks, you can use these functions that are shown here. Before you decide to use these reader writer locks in your processes, it is important for you to realize that these reader writer locks, they generally require much more overhead as compared to the semaphores or the mutual exclusion locks. And because of this excessive overhead, you should use them only in specific scenarios. So for instance, in your application, if it is easy for you to identify which threads or which processes are only reading the shared data and which threads or which processes are only writing the shared data. So if there is such a clear segregation, then it might be warranted. Now even then you should check whether there are more readers in the number of reader threads, are they clearly greater than the number of writer threads or writer processes. If so, then using the reader writer locks is warranted. If not, then it may be an unnecessary overhead in your application. Alright, so let's now think about, in the solution to the readers writers problem that we have devised, which of the two types of processes or threads has priority? Do readers have priority or do writers have priority? Now recall from our implementation. In our implementation, as soon as even one reader thread gets to enter the critical section, all other reader threads that might be waiting behind, they just fall through to the critical section. They do not have to wait for their turn to enter the critical section. Also, as long as there is at least one reader thread inside the critical section, any new incoming reader threads can continue to enter the critical section. And as long as there is at least one reader thread in the critical section, no other writer threads would be allowed to enter the critical section. So clearly in our solution, the readers have priority. And at this point, it is needless to say, in a heavily loaded system where there might be several readers and a steady stream of reader processes or reader threads keep coming in and entering the critical section, the writers may starve. Alright, so having said that, let's quickly think about how could we have given priority to the writer threads. Now one possible way of doing this would be, as soon as a new writer thread or writer process tries to enter the critical section, after this point no new reader thread should be allowed to enter the critical section. Those new reader threads which arrived after this writer has sought permission to enter the critical section, they must wait until the writer thread finishes executing its critical section. Now we can take this priority for writers even further by requiring that any new reader threads that have arrived, they must wait until there are no other writer threads that are waiting in the system to enter the critical section.